My name is Martin Monperrus. I'm with the Royal Institute of Technology in Stockholm, in Sweden. And I love papers. I love papers, and I'm even a professional paper lover, because being in academia, this is basically my job, to read papers and also sometimes to write papers. So I'm super happy to be here. Thank you very much, Renzo, for organizing this. Thank you, Derek Jones. Derek is not here, but so when I knew I would come to London, I shot you an email to, yeah, you're disturbed with that. And let's, oh yeah, I know my password. No, I don't know my password. Yes. So Derek Jones, when I knew I would come to London, I contacted Derek, said, do you know like a cool meetup in London to have a talk about Repernator? And Derek directly put me in contact with Renzo, and here I am. So thank you, Renzo, also because it's a nice room. So yeah, I love papers, and so for you, especially tonight, I selected 5 papers. So it's really a paper-oriented talks where I will talk about papers, not from me or from my group, it's from research in that field. And so what's this field about? So this is like the long-term vision, artificial software developer. So what's the vision? So today you have a code repository with 10 developers working on the code repo, you know, doing commits, pull requests, and so on. It works well, you know, you can have a flame war over a commit, but overall it works well. Now the vision is that tomorrow we'll have the same repo with the same 10 developers, a little bit older, you know, with maybe 10 years older from now. And we also have 10 robots working on the repo, you know, pushing code, proposing pull requests, reviewing pull requests, and so on. And maybe at some point we will have 10 developers and 100 robots working, collaborating together. So this is a vision. This is a vision. Robots and humans working smoothly together, cooperating together to build even more grand software than what we are doing today. This artificial software developer, it's a bot. And again, so if you say bot, it's not like a chatbot, which only answers to commands. So a chatbot, basically, it's a shell. No, it's here we're really talking of an entity, an agent, doing intelligent stuff. So this is in 10 years from now, not coming back to today. Today, what we can do in terms of intelligent agent is automatic bug fixing. So a bot which automatically fixes some real bugs. And this has a name in academia. It's a research field called automated program repair. Automated program repair. So it's like a subset of this artificial software developer, or like a very specialized artificial software developer. As we have today, we have developers who are specialized in fixing bugs. Tomorrow we'll have bots specialized in fixing bugs also. And there is already one artificial software developer, and here is his name. It's hard to read and to pronounce, I know. It's on purpose. It's Repernator. Repernator. It's a direct reference to a Hollywood movie, Terminator. And but Terminator is very negative. As I said, the vision is to have robots and developers, human developers, smoothly collaborating, working together. And so Repernator, you know, it's this nice robot. And Repernator is the code name of the project. He also has a human identity. I won't disclose it right now, but so there is also a human identity. And we'll come back to this later. So an artificial software developer works with the human developers, and in order to do something, and we will focus on artificial software developer fixing bugs. So this very idea of fixing bugs automatically was very seminal paper is this one. automatically finding patches using genetic programming. Wes Weimer, Tian Nguyen, Claire Le Guess, and Stephanie Forrest. An awesome team, University of Virginia, University of New Mexico, and so they worked together and did that paper in 2009, where it's really a revolutionary paper in a way, because there was decades of research to detect bugs. Detecting bugs with static analysis, detecting bugs with software testing, advanced software testing, so detecting bugs. There was also decades of research to prove the absence of bugs, all kinds of formal methods, model checking, and so on. But only them, and some related research at the same time, in parallel, they started to say, okay, we don't want to detect bugs, we don't want to prevent bugs, we want to repair bugs, because we have plenty of bugs. And indeed, we have plenty of bugs. We have bug reports filled with millions of opened issues. We have crashes in production, so if you open any log from production system, there are plenty of stack traces, So if you look at CI, continuous integration, well, you have usually 20 to 30% of failing builds. And so if you have like 1,000 builds per day, which is like a reasonable number in a large company, in a medium-sized company actually, so you have plenty of things naturally, plenty of bugs naturally. So you don't have to detect them. And so this was really a radical change in mindset. Wes, Tian, Claire, and Stephanie, they just simply looked at something new. And they did it very well. And they published the idea in the top, in a very prestigious conference, which means that this idea got some real visibility. And this started a new research field. Personally, it was really a shock. I really remember when I first opened this PDF. So the title was cool. I didn't attend to this conference. No, I didn't. But so I opened the PDF and said, wow, that's really cool. That's really mind-blowing. They automatically find patches. So just the first part of the title, automatic finding patches, is already really cool. And then using genetic programming. So there is this vision that you modify code automatically, and then you find a patch. That's even cooler to do this with genetic programming. So, you read this, you go to bed. The morning after, you say, wow, that was really a cool idea. And then you continue with your other research projects, but this is somewhere here, and you think about it and you say, wow, that's really impressive. And, and they did it in these initial papers, they did it for real bugs in C software, such as the PHP interpreter, the libtiff image rendering library. So like real code. So they didn't make assumptions with the toy language. They really considered real and hard and complex and deep software. I thought about this, and this basically changed my research life. Later on, so it's the idea continues in your brain, and later on I started to say, but I want to do this kind of research. So let's do it myself, and let's encourage my PhD students to work in that area and so on. So I started to work there, and then you start here at the very beginning, and now I'm completely drowned in automatic program repair. I'm not even able to talk about something else, and so I'm here to talk about this today. I'm sorry about this, but so this is like a seminal paper. They invented a research field. They created a new perspective. And they did it very well to start something, and so that's remarkable. Their system is called GenProg, for genetic programming. So the name lacks of originality, but so this is like key key paper. And you know, as anything which is good, it has to be somehow controversial. And right from the beginning, this paper was controversial. It was hard to get accepted. During the session at the conference, many people, you know, they stand up and say, wow, but it's impossible to generate patches, it's too hard, the search space. The search space, it's a key term here. So, you know, we know what a bug is, so we have a build failure, for instance. But then, so to repair it, we find a patch, and so what's the search space of possible patches? So it's basically all possible edits to the program. All possible edits, you know, it's potentially infinite. And indeed, it's really, really large. The theoretical search space for finding patches is infinite. But the whole point of this line of research is to define a way to have a smaller search space, a targeted search space. And if the search space is targeted, then you can use your full computing power on your machine, on a server, to explore it. So you can't explore all possible edits, but you can explore the most likely ones. But at that time, and still today, some people do believe that it's impossible. You know, the search space is too big. What you're trying to do is too hard. So one other thing in that paper is a problem statement. So I already talked about this. So basically what we need a bug. Or we can even be, so let's be academic. To do automatic repair, you only need something which tells you there is a bug, there is no bug. It's a binary procedure, you know? There is a bug, there is no bug. There is a bug, there is no bug. There is a bug, there is no bug. So this is something called an oracle. You know, there is an oracle telling you there is a bug, there is no bug. And the core idea is super simple, okay? So at the beginning, I have a bug. So I start with, yes, there is a bug. Then I try something, and I ask the oracle again, is there a bug? Yes, there is a bug. Oh, okay. So then I can try something else, maybe having learned something from my initial trial, you know? Is there a bug? And so that's as simple as a while loop, asking the oracle, is there a bug? Yes, there is a bug. I do something else. Is there a bug? Yes, I do. And at some point, the oracle will hopefully say, there is no bug anymore. Wow, cool. The bug is fixed. Excellent. So extremely easy idea. What kind of oracle can we have? You know, like a failing test case. I have a failing test case. It's binary, you know, it's failing or not failing. It's failing or passing, failing or passing. So I have a failing test case. I try a patch. Is the test still failing? Yes, okay, I start again. And so as long as my test is failing, I continue the search, and at some point my failing test case passes. Cool, I have a patch. This is test-based repair, driven by tests. And the thing is that I have failing test cases, but also I have passing test cases. So I have one failing test case and 900 passing test cases. So of course I want so I have this oracle. There is a bug, there is a bug. Oh, there is no bug. And when there is no bug, according to the failing test case, I run the rest of the test cases to see whether there is a regression. So because if I fix a test case but I make another one fail, that's not a success. So this is the problem statement in that paper, test suite based repair. I have a test suite. So this is a specification. This is an executable specification. I have at least one failing test case in the test suite, and I want a patch such that all tests pass. Very clean problem statement, you know. You can even write it with Greek symbols. Very nice. Test suite-based repair, invented by Wes and colleagues, and very good.
Aware of the Arcuri paper that's in
Yes. So, you know, in science, things are never invented at a single place. So things appear in parallel in different research groups. and so on and so forth. So indeed, there was one young PhD student, Andrea Arcuri, who had a very related paper 1 year before. There was also other, you can find traces, I found traces of this very idea back in the 90s. But you know, sometimes, so there is a difference between stating an idea somewhere in a sentence, in a paragraph, in a paper, and making the idea like flying and creating a new research community. And so this paper is the one which really created the research community. And the research line, and maybe even which will have this impact on practice. Any questions so far? Yes?
Is it possible to, instead of, well, I don't know if there's other papers that are talking about it, don't do this, but instead of treating it as a search problem, treat it in some other kind of aspect?
Yes. Then, yes. In short, yes. The thing is that, for instance, I think in the next paper, they use some kind of constraint solving, you know, with SMC solving. And so then it's not a heuristic search, but to me, it's still a search. It's just a search that is guided in a very certain way by the solver. But to me, it's still a search. So I would say that everything is a search, but in a different way of searching. This is really heuristic, and there are other ways of doing it. And it also very much depends on your specification, whether you can leverage your specification. If you consider test cases, this is somehow limited to drive the search in certain ways. But if you have other things like, you know, an invariant, a precondition, a postcondition, this is better to drive the search in another way. Does it answer your question?
Yeah.
Yes?
What's the function of this programming? Because if the success is binary, then you cannot rank your solution.
Can you repeat the question?
Yeah, and it's a very good question. The question is, what is the fitness function? Because if the test case is binary, then you have no search. That's a really, really good question. So the basic fitness function is a number of failing test cases. So it's a discrete failing function, discrete fitness function. And so if you have only one failing test case, basically it's one and then plus the regression and so on. So it's discrete. It's really bad for driving the search. And long story short, at that time, back in 2009, people really believed, and including the authors, they sincerely believed that there was indeed a search driven by the fitness function happening. It turned out that actually there is no, so in that kind of technique, there is no search happening. It's really random search. So there is no guided search happening with the fitness function. It's random. It's pure random search, but it still works. And to overcome this by dividing a fitness function which is more continuous. So you need basically two things. You need a fitness function which is continuous. That would be very good. Differentiable, it would be perfect, you know, but we don't have this. And you also need repair operators which provide small changes according to the fitness function, which we don't have because in a program, if you consider C programs, Java programs, a small change in the program can have a huge change in the behavior. A small change in the program can have a huge change in the behavior. It's not continuous. Because inventors of programming languages, they never thought about this. But it's terrible for repair and for driving the search because, you know, sometimes I go very close in the, so I do a very small change in the program, and actually I'm completely way off for finding a patch. And so, but yeah. Yes?
So you mentioned that in this paper they proposed some fixes for real software.
Yes.
How big were those patches?
One-liners. And today, 10 years later, it's still one-liners. Short. And so then the significance of this research is the amount of one-liners in your repo. Typically, you can find between 5 and 10% of one-liners in your repos. So see what you would do. Yes?
Maybe you want to clarify between patches and fixes. These were patches, not fixes.
So then, please define the difference between both.
For me, a fix is something that removes a bug. What they found in that paper and some follow-up papers was basically they patched the program that the failure wouldn't occur anymore. They couldn't observe the failure any longer. But how they did that was mainly removing the error checks.
So I will come back to this. That's perfectly correct, but I disagree on this terminology between patch and fixes. So it's a matter of definition only, you know.
Yeah, fix is something that removes a fault.
So yeah, according to this definition, which I disagree on, it's indeed defined fixes. Okay. No. So to me, you know, a patch is really a Unix patch. You know, something which ends by .patch, which you could apply to your software and you could compile and run the test again. This is my definition of patch.
Yeah,
That's
that's
you
a
mean
patch.
an edit script.
Yeah, a Unix patch. You know, I'm a Unix person, so that's important. Ready for the? So I have 5 papers. This is the first one. Ready to move? Yes.
Okay, so in practical sense, how long it takes for it to find a patch? It depends on the size of the program.
Yeah, it depends on the size of the programs. It depends on the size of the test suite.
Yeah.
Between 5 minutes and 1 hour.
For how big is the program?
You know, for a 50K lines of code program, you know, order of magnitude. It can go. Sometimes it goes faster. It really depends. But this is the order of magnitude. Yes.
Sorry. You mentioned that you used the search space by only looking relevant lines,
Yes.
but you also mentioned it was one-liner changes.
Yes.
Does this mean that the search space was essentially like one step ahead of the current code? Or
Very good question. So it means that the basic definition of the search space is the number of executed lines by the failing test. You know, if the failing test executes 1,000 lines, it's 1,000 potential locations to create a patch. But then for each line, it's all possible patches that you can get from this line. And this is huge. And so it starts by removing the line. You know, it's a basic patch. You know, you remove the line. And then, you know, changing one single variable or literal in the line, and then completely replacing the line by another line. So you have really those 2 search spaces, one after the other. Location and patches. Location and patches.
if we think it as a graph, it's essentially the tree of height.
Yeah, you can put it this way. Yeah, so there is a vision, and there is some research trying to do these multi-line patches, you know, like depth of line 2, you know, having a real search. I'm making a step towards the solution, but so far, to my knowledge, nothing works. For real, you know, it works on the paper, which is why we love papers, because it works on the paper, you know, but it doesn't work for real. Yes.
It seems that you're considering changes in the whole program, fixing the failing test. But the digital workflow is now every software is version control, so you can have successful days. So the patch is quite small for the last successful version of your software.
If it's a regression, yeah. So in some cases, so if you only consider regressions, then indeed you drive the search by the past changes, okay, with some kind of advanced git bisect, and you find exactly what you want. But in some cases, so there are different use cases, but you can also consider that you have a bug report, and the developer writes a failing test case, and and this bug was here forever, so then you can't look at the history to fix the bug. Yes?
Is it possible to think about like a missing feature as a bug, and the program can create new code?
Yes. Yes, so the vision of this artificial software developer, it's exactly this. We will have the artificial software developer creating new code, creating new features. There is also some very good research about this. It's called like program synthesis. And it's like program repair, it's one-liner code. Today, program synthesis also for real, it's short programs, but it's still real features, real functions, yes. And it's really a sister research field. So we share many concepts, we share many tools. So it's really related. Program synthesis and program repair, it's really close. So one way of putting this is, program synthesis, you don't have the answer. Program repair, you already have 99% of the answer, which is the existing program. But in both cases, you have a specification and you try to change the program.
Can you explain what you mean by you don't have the answer?
So program synthesis, you only have the test suite. You have absolutely no code.
Yeah.
This is what program synthesis is, like the pure version of it. So you only have the spec. You don't have the code. In program repair, you have the spec and the previous version of the program. So we already have much of the solution. Ready for paper 2? I don't remember which one is it. Of course, so it's something related to some advanced search. So so there was GenProg is really heuristic based, and here I also chose the paper so that they reflect the research field somehow. So GenProg, USA, University of Virginia, and University of New Mexico. Now we are traveling to Singapore. National University of Singapore, Tien, I don't remember his first name, and Abik, my colleague Abik Rochudori at National University of Singapore, 2013, so 4 years after 2014, and they published this paper, SemFix, program repair via semantic analysis. And they present the paper. It was this conference on software engineering research. This was the first year where there was a full session about program repair. In 2009 it was a single paper. 4 years later, it was like a full session with three or four papers, including this one. And so here they do. So it's the same problem statement, test cases, test suite-based repair. But the kind of search is completely different. What they do is that, so first they don't go over one statement after the other. So they don't iterate over executed statements to find potential locations. They do symbolic execution to identify one place where the patch should be. So they introduce a symbolic variable, they do symbolic execution, then they find, okay, if according to my assertion in the test, if I change this integer expression in the program, I would pass the test. The first phase, it's also fault localization, but it's fault localization based on symbolic execution. And then what they know that at line 42, there is an integer variable, an integer expression, which is buggy. And I know that for the failing test case, it should return 3. Before it was 2, and there is a bug, so the failing test case shows that it's a bug because it returns 2. But if this expression would have returned 3, the failing test case would have passed. So it's a patch, but it's halfway towards the patch. We know a value. Okay, if I have this value, then I pass the test. So then the problem becomes, okay, I want an integer expression according to the variables in the current context, the current scope. I want an integer expression which returns 3, given all the variables. And then, if this exists, so if I combine all the variables in my current context, plus, minus, divided, division, and so on, and it returns 3, wow, cool, my failing test case would pass by definition, because I know, thanks to symbolic execution, that 3 is a value to have. But we also have the same thing, because this very line is executed not only by the failing test case, but by other test cases. And you know, and so this expression, it returns 3 for the failing test case, but it returns 100 for another passing test case, or it returns 1000 for a third passing test case, and so on. The same expression. And so now I can have a conjunction over all test cases. I want to synthesize an expression which returns 3 for the failing test case, because we want to repair the bug, and which returns the same value as before for all the other tests. And this is exactly a synthesis problem. It's exactly a synthesis problem. And what they do in this paper is that they piggyback on other research in code synthesis, another paper, Oracle-based program synthesis, to generate such expression, returning 3, 100, and 1000. And I love this. I really love this paper. I remember this very well because I thought it's this. You know, this two-phase repair. First, identifying the effect on the computation. I want to have 3, and then synthesizing the code. It's elegant. It's really elegant. And today, a couple of years later, this very idea is still valid. And now this year I'm formulating it a little bit different. I call this deletion-based repair. The idea is that you delete a piece of code somewhere, a small piece of code, again, one line, one statement, one expression, okay? And then you synthesize it again such that it passes all the tests. Deletion-based repair. And then, and you can use super powerful synthesis techniques such that it works, but it is the very same idea that you delete something and you resynthesize it. You know? And what's really beautiful also here is that we are talking about real software, you know, real software in Java. So I mentioned 50,000 lines of code, 100,000 lines of code, so something serious, standard, full-fledged Java or C code. So of course, it's huge, but if I delete a single, one expression, you know, one statement, maybe a block of 2 lines, then this is small and doable. And so I really have this nice jump from a very daunting problem too big to something smaller that we can achieve. And when you think like this, it starts to give you also the kind of fault types that can be repaired. So for instance, I can delete an if condition. And we all know, we have all experienced a bug where the bug was you know, higher or equal instead of higher in an if condition. You know, enough by 1 error in an if condition. So I can delete an if condition and replace it with something else. And then it's so when I say this, I have a very clear definition of the fault type addressed by the system. It's bugs in if conditions. Or arithmetic bugs, you know, I know that my bug, I'm working in a domain where there is a lot of arithmetic expressions, x equals y plus z, y plus z minus 2, and so on. And we all know in such domains that many bugs are that indeed the expression is incorrect. And you want to resynthesize an arithmetic expression. Or, you know, floating point expressions. We have an expert here, my friend and colleague Earl. You know, floating point arithmetic, sometimes it's really hard because you have some very corner case effects, cancellation, and so on. So you lose some precision. And so in this case, you want to rewrite the expression so that you are not impacted by those effects again. And then the fault type, it's floating point errors. So here in this paper by our colleagues from National University of Singapore, really they introduce this really nice principled two-phase repair, and at the same time they also introduce a way to have a clear definition of the fault type. So in this paper they addressed Boolean expressions and integer expressions. And then we built some other systems, but again, so that's SemFix, program repair via semantic analysis.
In the presence of side effects, for example.
Awesome question. It doesn't work. This kind of techniques and this very technique, SemFix, doesn't work with side effects. Yeah, sure. Good. Paper number 3. An analysis of patch plausibility and correctness for generate and validate patch generation systems by Key, Longfan, Sarah Schur, and Martin Reinert from MIT. Big players in the game, 2015. So we are 6 years after GenProg. 6 years. What I didn't say about GenProg is that they had an open science approach. They published their tool, they published their benchmark, they published their patches, which is remarkable and which is key for doing good science. And you know, so these are students of Martin Reinert, professor at MIT. And so they started to do research in that area, and they started to look at the patches, to look at the system, and so to doing this analysis, okay, and this manual analysis, really looking at the patches and say, okay, what? And so we were coming to Jens' remark, whether it's a patch or a fix. So they looked at the patches and they realized that in this GenProg benchmark, most of the patches were either purely removing code, so yeah, commenting the buggy line, basically, or replacing the buggy line by another line, side effect free, which in effect is equivalent to removing code. Okay, and so they started to really to see that, to count the number of occurrences and say, but come on, so. In that very benchmark, it's most of the cases it's an incorrect patch. Correctness. It's an incorrect patch. So it's correct according to the test suite. It's adequate according to the test suite. But it fails to generalize to what the bug is and what the correct patch is actually. So we say that the patch is test suite adequate or the patch is plausible. It's plausible, but it's incorrect. Oh, that's really bad because, we were really happy in 2009 to have a well-formed problem statement. We have those test cases, test suite, and we generate a patch. And now we realize that this problem statement is not enough. And now we can step back. So, because this paper was super controversial, both in the content and also in the style. Because basically they said that GenProg 2009 it was not sound in a scientific way, in a scientific manner. Now reflecting about this, so indeed, okay, so a patch can be incorrect. That we can understand. Because we know that an input-output specification, a test suite, it's incomplete by definition. We know we don't cover all possible inputs, and we will never cover all possible inputs for any reasonable software. So that's normal. We know that. But what we didn't know, and what we still don't really know today, is how strong is this incomplete specification to still drive the search somehow. So, or in other way around, what's the likelihood of generating a plausible yet incorrect patch? Or put in another way, how many plausible yet incorrect patches are there in the search space? Okay, are there a single one patch, and then it's bad chance to find it, or 2, or 100, or 1,000? Nobody knows. the degrees of freedom, you know. So a patch, basically, it's using the space of freedom in the computation provided by the test cases, you know. And this is where you actually change the behavior and find a patch. And so how many degrees of freedom do we have in the search space of possible patches? We come back again to what's a repair operator, what's the syntactic neighborhood, with the functions. Anyway, my point is that at the very beginning, the initial GenProc team and the initial followers, everybody thought that, okay, it's super hard. We know that it's super hard. It's hard to find a patch. But if we find one, we're done, you know. We've done the job. It's really cool. So people thought that it would be super hard to find one, and that's it. Here they realized that actually, so it started to realize that it's not that hard to find one. Indeed, just by removing code, you know, by removing code, you find a lot of patches. Even with very well-tested code, you would be surprised. You would be surprised how often you can just by commenting out code. And then with other papers, what we realized is that the problem is not to find one patch. Again, we can easily find 1, 10, 100 patches, 1,000 patches. So I told you about Reapernator. So Reapernator is one of my my good colleague in my email box because it sends me emails each time it finds a patch. It can repair a bug, a real bug happening on open source. And sometimes I receive an email with, for a single bug, a single failing build, I receive 1,000 patches, you know, patch 1, patch 2, patch 3, patch 4, patch 5, so on and so forth. So the space of patches is really huge. So here, this paper is key in the field because they say, come on, it's not enough to only look at test suite adequate patches. If you aim at correct patches, you want to do more. And this is super hard because, you know, then what's the oracle of doing more? You know, so how to assess the correctness of a patch? So of course I can analyze it. You know, I can ask my PhD student to look at the patch and say, okay, is it a correct patch or not? But this is not satisfactory. This doesn't scale. This is subjective. You know, imagine. Imagine some of you are in academia. So you're in academia. You're a PhD student, and you will get a PhD if you get a paper accepted. You invent a new program repair system. It's really good. It's funky. And you evaluate it, okay? To evaluate it, you take real bugs from open source project, and you run your system on those bugs. So far, so good. You know the literature, so you read this paper, and you know that, okay, it's not enough if the patch passes all tests. So then what you do is that, okay, I will analyze the patch manually to say whether it's correct. And here, even if your research ethics is perfect, somehow you still have an implicit bias towards saying that the patch is correct, because it will help, you know, your paper, it will help your PhD and so on. So we need other techniques than manual analysis, or if it's manual analysis, we need it to be done by an external, unbiased person, ideally the developer of the software under repair, but usually it's a very busy open source developer, so it's hard. So this paper, it's a really good paper. What I'm always saying to my students is that a good paper, it's a paper which calls for other papers, you know. It's generous for research. It doesn't close doors, it opens doors. Okay, and this one basically they stated a lot of problems. Okay, so we have the problems of incorrect patches, we have the problems of manual analysis, we have plenty of problems. And so if you are negative If you are pessimistic, you can say, okay, let's stop this jog and let's go to another research topic, you know, where it's easier. But no, because we want to know Reapernator. We are only in 2015, so you know, Reapernator didn't exist at that time. So let's continue. But here we know that a patch can be plausible and incorrect, and we call it an overfitting patch. Overfitting is a word coming from machine learning, which means that basically you were very good at training time, but when you go to testing time, it's not good anymore. Here it's overfitting to the test data. Okay, so the patch, the patch generation system is good at tweaking the computation to get all tests passing, but it fails to generalize. So it's an overfitting patch. Overfitting, but it's still an open research problem. Overfitting patches, it's super hard. It's super hard. Any questions? Yes?
So if the problem is that you can't represent every case in test cases, is there any research on kind of formal specification languages like PLA plus and stuff like that?
Yeah, definitely. So there is some research on using other kind of specification, and this solves many problems. But the price to pay is applicability on any arbitrary Java or C or whatever software.
So this is specifically going for just Java code.
No.
Like
The problem statement here is so as I said at the beginning, you need a specification. You need an oracle and Reaper operators. So then you can do with whatever specification. If you do test suite based Reaper, you only assume a test suite. Okay. And then if you want to consider other kinds of specification, including logical formulas and logics, then it also works. It depends on what you want to. So Reapernator wants to repair arbitrary Java software on GitHub. And for this, you have test suites, but you don't have a stronger specification. Yes?
Some languages have property testing tools where you can specify the properties and they randomly.
Yes.
What's the test that you're going to?
So that's
can generate more tests.
Property-based testing. It's the future of program repair in practice, because indeed with property-based testing you have a way to explore the input space, and it's super valuable. It's getting some momentum in industry and in open source, which means that today, if you look for open source projects with a good property-based test suite, it doesn't exist. So I don't know one, but so if you know one, please send me an email. Yeah, so there are tools for doing this, but users of property-based testing. This is what I'm. So there are tools, very good tools, and it also depends on the software stack. So if you are an Erlang or Elixir programmer, it's likely that you've already written a property-based test. But you know, an average Java developer doesn't write property-based tests or parameterized tests, which is equivalent to some extent. So, but yeah, so hopefully, you know, today we teach our students to do that, and in 5 years from now, we will get software with property-based tests. That would be really good. That would be so. And side note: if you write tests yourself, please consider writing property-based tests. You know, adding one quantifier over your test, it doesn't cost much, and it gives you much, I would say, in terms of testing. Yes? Fourth? What's the fourth? Oh yeah, I know we are going into the fun. The robot scientist Adam. Done here in the UK, Rosking and colleagues. So it's not anymore. You know, this paper, it's not a software engineering or programming language paper. It's a functional biology paper done by a team composed of both biologists and computer scientists. So Rosking is trained as a computer scientist. And so what they do here, and so they want to know, they consider the bacteria, I don't remember which one, and they want to decode the genome of the bacteria. And so basically what you want to do is you want to understand the impact of a gene on a specific protein at the end. And so here the search space, is all possible proteins can be encoded with the genes you have. So it's a huge search space. And so what they do in the lab is that, okay, they devise a hypothesis. So okay, I assume that this gene has an impact on this protein, and then I devise the experience. I do the experiment with some statistical test, and then scientific method. I loop in order to refine my knowledge and so on. But this is super heavy work because you need to set up the full experiment. You need to have the reason. So you have the analytical reasoning over the genes and the proteins, and you also have the concrete, dirty hand work on putting everything on in the lab and doing the experiment. The vision of Rosking and colleagues is that you can automate this. You can build a robot which has both this understanding, this formal understanding of the gene space and the protein space. And it's also a physical robot which can take a specific liquid here and a specific bacteria here, put everything together, put it in the fridge, put it in the oven. I don't know. I'm not a functional biologist, but you can fully automate this, doing the observation of the result of the experiment, and then doing the next hypothesis, and looping, and again, and again, and again, and again. Fully automated science. Fully automated science. Respect. Respect. The conclusion of the paper is that, in 100 years from now, the best physicist ever will be a robot. Must be the case. And so Adam, at some point, Repernator came to my office and said, hello, Martin, I read this paper, you wanted me to be an artificial software developer, but I really want to be like Adam, I really want to go in the wild and do something for real in the same. And this is where Repernator started. So Repernator, as I told you, it's an artificial software developer. And so in software development, we don't have like those real experiments in the lab, like in functional biology. We only have digital artifacts. But it's also very lively. And so here is the setup. What the bug-fixing robot needs. So it needs code. We know where to find code. On GitHub. That's it, it's on GitHub. Of course, you can put it on Bitbucket, but it's not serious, it's on GitHub. So we know where to find code. That's okay. Even in your company, it's in the company repository. We know where to find code. Repernator, he wants to repair bugs. So it needs also bugs. We also know where to find bugs. In any bug repository, you have plenty of. That's easy. But you need executable bugs. So you need a failing test case somehow, or something failing. And then we discuss with Repernator and say, okay, so where can we have failing? Because bug report by a human, it's not failing. You need another human coming in. And so Adam, there is no human in the loop of the experiments of Adam. It's fully automated. And so discussing with Repernator, we say, okay, we do have failures in continuous integration, in CI. In CI, we have plenty of failures happening all the time for good and bad reasons. So let's be Adam in CI. GitHub CI, okay, the number one CI on GitHub is Travis CI. In Travis CI, they are very nice. They provide a way to listen to all builds in real time, there is an endpoint in the API giving you all bits. Not all, 250. It's still good. So I can listen, yes. The problem with that is that, do you mean like the first line of code, or do you mean the idea, or do you mean the first operation?
Why not just say, have the answer be in inclusive order?
Yeah, in short, so we can have a very clear definition of starting. It's like when we really started the operation of Repanator live on GitHub, and it was in January 2017. But it was, like a baby Repanator at the very beginning. It was already listening to bits on Travis CI, trying to do something, but it was like a baby. Woohoo! It's hard. It's really hard. Take an arbitrary build on Travis CI and try to compile it locally. Poof, it's hard. Try to reproduce a failure, a failure happening in the data center of Travis CI, try to reproduce it locally. The same failure. If you take a reasonably sized Java software, so it's all in Java, Repanator speaks Java, it's hard. So this is what Repanator wanted to do, to be like Adam, and so Adam, the strong claim of King and colleagues is that they discovered new gene-protein relationships, something that is publishable, so it depends on what your actionable definition of discovery, but they really discovered new pieces of scientific knowledge in a fully automated way. Repanator, so what would be the equivalent of this? It would be to patch a real bug in a fully automated way. To be human competitive, So I like this term of human competitive because it gives you the bar to get, to be as clever as a human, to some extent, assuming we are human. This is not what I'm stating. We are clever. I think we are all human here. Is there a robot in the room? Maybe. I don't know. So Repanator wants to be human competitive, which means finding a patch as fast as a human. Because if a human takes 5 minutes, but the machine takes 2 days, it's not really competitive. It's a tour de force, but it's not really competitive. And also of similar quality. Humans don't write. Still okay. Repanator should find a patch of similar quality also. Yes.
Repanator can be the human, even if it takes 2 days, when a human would take an hour to bug that humans wouldn't fix.
Yes, correct.
You were underselling Repanator just there.
Yeah, I'm low profile, Earl, so that's yes, I'm underselling Repanator, maybe. But Repanator is modest, He has a GitHub profile, small contributions there and here and there. Talking about the contribution of Repanator, imagine, so you're an open source developer. You're an open source developer working on a project, and there is, you have a failing build. This happens in many cases because, many of us, we don't run the full test suite on our local machine. So it fails on CI, which is fine. A good test, it's a test that fails. Otherwise, you never learn something with your test. You have a failing build, and you start working on this, and then you receive a pull request fixing this failing build. How is that possible that somebody elsewhere in the world is looking at your build, at your own build? Next paper. Among the machines, human-bot interaction and social Q&A websites. Paper. Colleagues from University of Antwerpen, it's not a program repair paper, but it's a bot paper. As developers, we all know that a significant part of our development time happens to be on Stack Overflow. That's key, you know. And if it's not a Stack Overflow, we first go to Google, but Google sends us to Stack Overflow. So it's basically the same. So social Q&A website, it's Stack Overflow. Okay, and it's heavily used for programming. What we have on Stack Overflow is that there is a huge amount of results and answers. Often people ask a question which is a reformulation of a previously asked question. And so a lot of Stack Overflow contributors, they constantly say, okay, this is a duplicate of this question, this is another duplicate, or maybe you can look at this. So they link questions and answers together. Our colleagues at the University of Antwerpen, they say, okay, so let's build a bot to do that, to identify the answers, so given a new question, identify the closely related question with an answer and to propose this answer as answer to the new question. Okay? Because if indeed it's a reformulation of the same question, the answer to the second question is also the answer to the first question. And so they created this bot, and they started the bot. You know, the bot was autonomous on Stack Overflow, looking at new questions and pushing answers. And guess what happens? In 3 days, the bot was banned. And it wasn't banned because of the terms of service of Stack Overflow. It was banned because of its reputation, because people hated getting answers from a bot. I don't know, they felt offended, or they felt really, really bad about this. You know, I'm a human. I don't want to be taught by a bot. That's not what I want to do. So -1, don't vote. And I don't know the threshold today, but after seeing a large number of downvotes, you're banned. And the researchers, they say, okay, but it's strange because really the answers, they come from another answer, they are correct. So what they did is that they created a fake human identity. So it's the same bot, the same data, with a fake human identity. And this bot is still running, and a very high reputation on Stack Overflow, and so on. So here, program repair, we started in hardcore program language technology, and now we are with these human-bot interactions, So Repairnator can't be a robot when it first approaches a human developer. Maybe in 50 years from now, the people will be used to work with bots, and that's fine, but today it's not the case. So Repairnator has to have a fake human identity. So that as a developer, getting a new pull request on your favorite open source project, you see a new contribution coming from a new human contributor. And so this is Luc Ezapé. Luc Ezapé, it's the human name of Repairnator. And it's here only, to get accepted by fellow open source developers. Say, oh, cool, thank you for the patch. These kind of things. Or, yeah, that's hard. One of the feedback we got on one Repairnator patch was, oh, thank you very much. But could you please sign the license agreement? So we asked Repairnator, could you please sign the license agreement? And he said, okay, I want to go to the legal department of the university. And said, no, don't do that. Don't go to the legal department. We will sign it for you. So we, as Repairnator friends, we signed the license agreement. The patch was accepted. And then somewhere on the mailing list of the project, somebody claimed, wow, we have our first external contributor.
So When you signed that, did you check with the patch whether it is really fixed?
In this case, yes, and in this case, the external developer checked that before merging.
But you checked it, so you still have the human in the loop.
Correct. This experiment, correct.
You probably wouldn't have signed if you figured out, oh, there's something that has been overlooked.
Correct. Correct.
So,
Yes.
But is that the sort of sign dispatch just giving away the copyright to the
Yeah, exactly. Exactly.
It's not, because most software is anyway as is.
Exactly.
No one's responsible.
Exactly. It's not a matter of responsibility. It's a matter. Yeah. Exactly. But still, you know, so I'm not trained as a legal person. I don't know that. There is still an interesting question here, because code generation has existed for decades, and there have been legal cases of who owns the IP of generated code, and depending on the jurisdiction, on the countries, this has been solved. But code generation, there is no creative part in code generation. You can assume that, you know, it's a one-to-one relation between the initial artifact and the generated code. Here, we start to enter into the creative area. You know, you fix a patch which has never existed before, which is not a direct implication of the specification and so on. So somehow we come into the creative area, which is indeed so IP, Berne Convention, and copyright. Yes. Yes.
So a question actually about this paper here. Is there any measurements in the accuracy of the suggestions?
Mm-hmm.
Is there any measurements say what percentage of the suggestions made by the bot is written?
Yeah, I don't have the numbers in mind, but they are in the paper.
Do you have a rough idea if they are?
No, I don't remember. I don't remember. Yes. Sorry?
What about the
Repernator looked at 14,000 failing builds in Java, generated a patch for 120 something. Many patches were either too late, so after the actual human patch, or overfitting. Repernator created 13 pull requests, and 5 were merged and developers. Now we are coming to the conclusion slide. So Repernator is the first ever bug fixing robot operating on GitHub and Travis CI. So listening to the constant flow of failing builds and trying to repair them. It has produced 5 patches merged by the lead developers of the open source repositories. And you know, it's only the beginning. It's a one-liner patch, but this is a vision. Again, we are trying to build the future. And since it's super hard, it's an open and inclusive project. You are all welcome to join Repernator. Everything is on GitHub. Everything is open source. Everything is open science. You can try it on your own. It's research prototypes, but if you want to have fun, that's really fun. Very nice community. Repernator will go under an open source foundation very, very soon. So it's a community project. It's only the beginning of a super hard endeavor. And so you're more than welcome to join Repernator. Thank you very much. Yes?
How much CPU time has Repernator used so far?
We don't have the measurement.
Rough.
It's one server machine running full time.
Since when?
January 2017.
So 2 years.
Yes.
So we're talking about 2
Yes. Exactly. Yes.
What are the cases of chaos where the reviewer asks for changes
Yes.
and I guess you manually do the changes?
No, we stopped. We say, sorry, I can't. I can't. But the vision is that at some point, Repernator would have some conversational features so that it can improve the patch based on the questions and feedback on the pull request. We are not there yet. Yes.
So, have you considered, or anyone tried, approach of more like a learning type approach? So try to look at previously human examples, how they fix patches, and training example, and just try to provide patches based on that. So how successful is that kind of approach?
It's ongoing research. So if you want, I invite you tomorrow at UCL. I'm giving a talk on a learning-based approach about this. It's ongoing research. It works also to a certain extent, also for one-liner patches. So yeah, it's ongoing research. It works. But those 5 patches, they were not done with a learning-based technique. Yes.
Just one last in which areas you next goals for doing the book?
Learning-based approach, because the beauty of a learning-based approach is that it's very creative in the repair operations. And on the contrary, in many other systems, somehow there is some top-down design, intelligent design of the repair operations, which is good for achieving something, but it's a learning-based approach can really explore the full space of repair operations, even the rare ones, which is really good. So this is one thing. The overfitting problem, as I said several times today, it's not a solved problem. So, and we are doing research in catching those incorrect patches as early as possible in the process, and ideally, so always before reaching the human. We would prefer to propose less patches, but always correct, because we have this human-bot interaction, and trust here is key. And trust to a robot, it's super brittle, So 1, 2, 3 good patches, it's good, and then a single bad one, you lose everything. So we really want to have a very high precision, very, very high precision. And so for this, overfitting detection is key. Another thing that, there will be one student coming to work on patch explanation. We all know that in open source, only code is not enough. There is really a conversation with the human, and for this you need natural language, you need explanation, you need examples. And so Repernator has to be able, so far, on those 5 human patches, the explanation is that fix failing build. It's a little bit dry, It could be fix failing build, in this particular case, x equal 1, we should do this and that. So really having a high-level explanation of the patch, and not only a reformulation of the patch, but also showing showing example of the behavioral difference and so on, explaining the effect on the system. This is what you're trying to do. As I said, a conversational feature with the developer would be awesome. Maybe in a guided way, maybe the developer could ask specific questions. Can you consider this input x equal 2? Okay, and then you would have another patch. There is a lot of engineering to scale, again, because here we only target some subset of Travis. If we want to scale to open source, it's way more. So, short answers. And we can take it longer at the pub. It's up to you.